Hello, and welcome back to AP Environmental Science. Today we're going to start off with your first mini quiz question, and it will tell you what we're going to be talking about. So, which of the following covers the greatest percentage of the Earth's surface? Desert, tropical, forest, ocean, or grassland? Well, obviously the answer is ocean. And that is what we're going to be talking about today. Today I want to talk a little bit about marine ecosystems. And this covers about 3/4 of the Earth's surface. And when we talk about marine ecosystems, we're talking about oceans, coral reefs, and estuaries. So when we have conversations about estuaries, that is actually included in the marine ecosystem because in this case we're referring to anything that has higher salt than about 0.5%, maybe 1%. And so it's kind of two conversations when we talk about marine ecosystems. We divide it up into the oceans part and the estuaries part, but they're all marine ecosystems. Now, it turns out that in marine ecosystems, the primary producer is algae, phytoplankton. And they actually provide the majority of the world's oxygen supply. And in addition to that, in that very same process of photosynthesis, they take in a huge amount of atmospheric carbon dioxide. So in fact, the ocean is the largest carbon sink in the world. Right? It's the largest carbon sink in the world. And when we talk about carbon and we talk about climate change and things like that, we will talk about carbon sinks, right? But this is the biggest one. Now, here's the other thing that I think is fun about marine ecosystems. It is evaporation of water that actually leaves behind salt, and so the oceans are salty because water evaporates, and we've talked about water evaporating as a part of the water cycle, and we know that evaporation of ocean actually provides the rainwater for land. The majority of rain that falls on the land is actually from the ocean. But when that happens, it leaves behind all of the salt. And so that is how the ocean itself got salty to begin with. There's a fun little story there. All right, so let's talk a little bit about how the ocean is divided up. So the ocean, just like land, has different geography. It has elevation changes, right? Except in our case, we're going to go from sea level down, so we get deeper, and conditions change radically as you get deeper in water. So there are larger differences in environmental pressures going from the coast down to the deep ocean, probably more than there are when you go from the coast to the top of a mountain. Not saying that there's not lots of changes going to the top of a mountain, but water makes that really different. But it's a huge space, and there's lots of variation within the ocean. So we actually divide the ocean up into 4 big zones. The intertidal zone, which is going to be where our estuaries are. This is the area of land between high tide and low tide. Okay, so there's lots of changes. There's the neritic zone, which is the edge of that intertidal zone to the end of the continental shelf. And when you talk about continental crust versus oceanic crust, the continental crust is raised up, it's actually thicker, and so you've got this sort of slope on the edge of every continent. And we use that slope oftentimes to sort of gauge where we are because that's going to be the bottom at that point, right? And so that's our limit to depth. So the edge of the continental shelf to the intertidal zone, that's called the neritic zone. And we're going to focus on the neritic zone because this is where things like coral reefs and kelp forests are, right? The baffle zone is the edge of the neritic zone to the base of the continental shelf, okay? This is also known as the pelagic zone, and it's divided up into several regions, but we think about it as sort of like that oceanic zone. And that's really the majority of the ocean. Then we look at the very bottom and we talk about the abyssal zone. And this is actually anything that's going to be pretty much below the base of the continental shelf or out in the deep open ocean. And we're not going to talk about the abyssal zone at all in this. Right, but this is where really interesting stuff happens. We will talk a little bit about deep sea vents just because they're really interesting, and they are in the abyssal zone, but as far as the abyssal zone itself goes, we're not going to talk about it. Okay, so let's talk about the rainforests of the ocean, and these are our coastal water habitats. These are the neritic habitats in that neritic zone, and we're interested in 2 of them, the coral reefs and the kelp forests. These are the most productive marine ecosystems that you have. And so I'm going to start with coral reefs. We're probably real familiar with them in terms of the idea of all of the fish and all the wonderful things that you see in coral reefs. We also know that there are whole islands that are built of coral, right? Because we know that coral have that great calcium carbonate that they produce, and so they essentially have these little skeletons, and those will build land for all practical purposes. Okay, now usually, and the majority of coral reefs are found in shallower tropical water. They need high light levels. There are coral reefs in temperate zones and even moving up north into temperate zones, but it tends to be in the southern temperate zones and the tropical zones. They also have the highest diversity and abundance of all of the marine ecosystems in the oceanic system. So that we're leaving out estuaries here because estuaries, of course, are their own thing. But we know that coral reefs, highest diversity, they actually have more than 25% of all ocean species. And we look where they are, we can actually see that there are lots and lots of coral reefs around the world. Now, unfortunately, they're really fragile ecosystems as well, right? They're really fragile. And so we want to talk about the state of coral reefs, and that's going to be the focus of our class. So let's shift a little bit though and talk about how do we build a reef. So the reef itself is actually formed by coral polyps. They're tiny little animals. They live in colonies. So what you're looking at when you look at here is actually a whole series of little animals. And they form hard, stony, branching structures made of limestone, and that's their anchor, right? So here's that limestone structure. And over time, as the little polyps die, they're going to leave layers of this calcium carbonate that they're building. Okay, and new polyps will attach to the old coral, and that's what builds the reef. And we'll talk about this more later on as well. Okay, so what are some threats to coral reefs? Turns out that there are lots of things that damage coral reefs. I told you they're very fragile, so a lot of the activities that we do actually endanger coral reefs, and it can range from stuff like pollution and oil spills to overfishing, boats, just walking around on them, doing construction, dropping anchors into them, divers for tourism. So lots of the things that we do affect them. Also, natural stuff does too. I mean, storms will break coral reefs, things like that. Sediment that washes in from rivers. So let's say you have a high precipitation year, you get a lot of extra sediment, that can damage coral reefs. So they have some natural threats too, but there's a lot of stuff that we do to them, and we'll continue talking about them. But one of the worst things that happens to coral, obviously, is that it dies, but coral bleaching is something that's happening all around the world, and it's where these beautiful, rich coral ecosystems, the little polyps die, and then what you have left is just a whole field of skeletons of coral. And we'll talk more about this and why does bleaching happen and what occurs and why is it happening so much more frequently now than it used to be. Okay, so let's switch and look at kelp forests. Kelp forests are going to be found pretty exclusively in temperate zones, right? And they go pretty high. They'll come into the southern polar zones. They also need really high light levels, but instead of being dominated by coral, which is an animal, right, the producer in the coral reefs are going to be the phytoplankton. The producer in the kelp forests is giant kelp and is this huge algae, right? It has extremely high productivity, and like the coral reef, it is a large fishery. So when we talk about the fishing industry, we are talking about a lot of that fishing is going on around or in coral reefs and kelp forests because you have such high productivity there. Now, there's also open ocean fishing too, right? But a lot of it is going to be near or in these two ecosystems. Oh, and this is a cute little otter. We'll talk about them as well. Otters are very important in the kelp forest. Okay, so what happens when you get beyond the base of the continental shelf? You are in the open ocean. The swimming part of the ocean is called the pelagic zone. The bottom ocean bed, whether it's on the continental shelf or it's on the actual ocean floor, you're talking about the benthic zone. So life in the ocean can be divided into the pelagic community and the benthic community, the bottom dwellers and the swimmers. Okay. Now, the thing about the open ocean is that it's deep, and so it actually has lots of variety in the different kinds of factors that are playing in. You've got light level, you've got temperature, you've got salinity, and you also have pressure. Deep water stuff, really deep water stuff, when you bring it up to the surface, has a tendency to explode because it's used to having all of that pressure on top of it. I mean, you're talking about pressure that's intense enough to crush like ships and things. That's why submersibles have to be so well constructed. Yeah. The zones themselves, though, are divided based on light levels, just as an aside. All right, the last community that I want to talk about are just one more note on the open ocean. There's a lot of marine species, but there's not a high abundance out in the open ocean. And so the open ocean is actually a lot like, biodiversity-wise, a desert. Just saying. Okay, so the deep sea hydrothermal vents, what's fun about these is that they are fairly rich communities. There are a lot of nutrients here, and there's a lot of hydrogen sulfide, which chemosynthesizers can use as an energy source. And so you end up getting these very rich communities with these little deep sea guys on these hotspots on the ocean floor. And it's very likely, or at least one of the hypotheses about the origin of life, is that little chemosynthesizers might have evolved here in deep sea vents. And so this might actually be the starting point for all life, and that's kind of a fun thing too. But in the grand scheme of things, most oceanic species live in or near the coastal zone. They live near the coastal zone. Okay, so let's shift a little bit and talk about the properties of seawater. Seawater is different than freshwater, and here are some saltwater facts. Seawater is less than 97% pure water, right? And so 3.5% or so of salt water is actually dissolved solids and gases. And that's going to be everything from the stuff you expect, like oxygen and carbon, to the salt, right, that you also expect, but there's also nutrients and sediments and other gases. And the physical properties of salt water are the same as pure water, right? But they also have some of the properties of salt. Pure water, for instance, does not actually conduct electricity very well. Like if it has nothing else in it, if it's just H2O, it doesn't actually conduct electricity. But once you put some salts in there, it conducts electricity really, really well. Right? The things that we measure about ocean water are going to be things like salinity, temperature, pH, nutrients, dissolved oxygen, turbidity. Those are the big five, right? Salinity, temperature, nutrients, dissolved oxygen, pH, oh, that's six, sorry, pH, and turbidity. And turbidity is clarity. Okay, so ocean circulation is something we also want to talk about. I'm not going to talk about it right now, but that variability in salinity and temperature is the key to mixing, right? It's the key to current flow, both vertical and horizontal currents. Wind, of course, is going to help with the horizontal currents, but salinity and temperature are the big drivers there. Okay, so how do I know if all water has salt in it? How do I know the difference between freshwater and saltwater? Freshwater is defined as having less than what % dissolved salt concentration by volume? It's actually less than 1%. All water has a little bit of salt in it, right? Remember, that's how the oceans got salty to begin with. But less than 1% is saltwater. In order to be briny, you have to be a whole lot more than that. As a matter of fact, freshwater is 0 to 0.5 parts per thousand. Salt water is going to be 30 to 50 parts per thousand. Okay, and then I've just put in here, you can see some of the different, we know that a lot of that salt is just regular old table salt, right, sodium chloride, but there are also your magnesium chlorides, calcium chloride, sodium sulfate, and then there's a bunch of other like trace amounts of other salts. Okay, and it turns out that I told you that there were differences in the surface salinity. When you have these warm waters, they are saltier than the polar waters for a couple of reasons. One, warm water holds more stuff. This is something we learned in chemistry. So think about if you want to dissolve stuff into water, you heat it up, right? That's how you get saturated solutions. You can increase that level of saturation by heating the water up. The water at the poles is a lot colder, and you've got ice that's freezing and melting, right? But mostly it's about temperature, right? Warm stuff holds more stuff than cold stuff. Speaking of temperature, temperature is going to increase with, or decrease rather, as latitude goes towards the poles. Temperature is going to decrease with the depth of the ocean, except where salt is formed. And by the way, or sorry, except where ice is formed. And by the way, the water under the ice as the ice is freezing actually increases in salinity, but that sinks to the bottom. And so the surface water is actually less saline because the really saline water sinks to the bottom. And we'll talk about how that works when we talk about ocean circulation. But ultimately, ice does not have salt in it. And so, like when water evaporates, it leaves behind the salt. When it freezes, it leaves behind the salt. And here is a map of surface temperatures. It's exactly what you expect. Equatorial regions are warm, polar regions are cold, and you get sort of a scale in between. All right, that is it for this conversation about marine ecosystems. We will be looking at that more in class, of course. If you have any questions, please don't hesitate to ask them. Thanks for listening, and I will see you next time.